So we've covered all the content we need to cover for Unit 5 now. For this video, I'm just going to go over some different types of problems. So this will all be stuff you already know how to do. What I suggest doing is pausing the video and trying the problems on your own before you watch me do them. I think it will be more beneficial for you that way. So here we have just regular delta G. We are looking for delta G of this overall reaction, and we have delta G of formation for NO and NO2. So what you want to do here is write the formation reactions. Now remember, the formation reactions, this was a while ago, the formation reactions are always for 1 mole of whatever this substance is from its elements. Okay, so for NO, we'll have N2 plus O2 gives us NO. And then you want to balance it, but you can't change the coefficient of this because the formation reaction is always going to be 1 mole. So that means you would have 1/2 here. Whoa. And 1/2 here. And then I'm going to do the same thing for NO2. And if you're wondering why I'm doing N2 and O2, that's because they're diatomic, just to refresh your memory. Oops. And then here I just need 1/2 right here because it's O2. And so I have these delta G of formation values. So what I can do is use Hess's law to get my overall reaction. Okay, so if we have NO here, and it's only in one place right here, so what we'll do is reverse this reaction and multiply it by 2. So we would have 2NO gives us N2 plus O2. And then we'll do the same thing to that delta G. You're going to reverse it and multiply by 2, so that's 174. So then for the next reaction, we actually don't. So for this one, you actually don't even need the second reaction because once we reversed this and doubled it, we got the overall reaction we wanted. Okay, so they just gave you this for extra fun, I guess. So your answer here is going to be that, kilojoules per mole. So let's take a look at this one. Okay, going to be the same basic idea, except this time we have a different overall reaction. So I'm going to write my same 2 formation reactions. So here I want to keep NO2, but I want to reverse NO. So if I reverse NO, and then also reverse that delta G, so now it's negative 87. You want to keep the NO2 one. So you'll keep that delta G the same. And then we can cross out this N2. This will go away and we'll have 1/2 here. And so our overall reaction is what we were looking for. So when we add those delta G's together, we get the delta G for the whole reaction. So just a little Hess's law refresher. Okay. So here's the same deal with Hess's law. So if you haven't been pausing the video, this would probably be a great time to do that, get some practice. This is delta H, but it's going to be the same basic idea. So now we're going to have some more Hess's law problems. If you haven't already been pausing to practice, I would recommend doing so. These are going to be related to delta H, and some of them are going to require you to think a little bit more, but you can totally do it, so give it a shot. So this one says, given these two reactions, how do we find the delta H of formation for SO2? So the first thing you're going to want to do is write the formation reaction. So remember, for SO2, we want 1 mole of SO2. So that's our formation reaction. So this is going to be our overall reaction. So if we go to the two reactions they gave us, we're going to keep this one. So we can keep S. And so that delta H is going to be the same. And then for this one, you're going to want to flip this so SO2 ends up as a product and multiply by 1/2. So then our SO3s will cancel. Oh, this should be, yeah, 1/2. And then this will just become 1O2, which is what we wanted. So our delta H, when we add those together, we get 296, negative 296. All right, so here is another one. And they do give you the overall reaction, but there are 3 here. And I'm not going to go in order here. Okay, if I do go in order, you'll see automatically that I have no idea what to do with this first one because I don't have O3 or O2 in my overall reaction. So I'm not going to look at that. So I can go to the second one. We have O, single O by itself. It's only in one place here, and it is in the overall reaction. So that means I'm going to have to flip this one and multiply by 1/2. And so my delta H will become this. So then I'll go to the third one. I have NO, and that's the only places NO has. Also NO2, so we don't have to do anything to this one. And so our delta H will stay at negative 199. So now we can go back up to the first one. Okay, so that first one is to cancel stuff out that we do not want in our overall reaction. So you can see we have O3 here, and that's the only place we have O3, but it is not in our overall reaction, so we need to cancel out this O3. To do that, we have to flip this, but then also multiply by 1/2, or we'll end up with O3 again. So we want to flip and multiply by 1/2. And do the same thing to our delta H. So I'll double check to make sure I did that correctly. Our O3s cancel. And then we have 3/2 O2 right here, which will cancel with this. So we got our overall reaction. So once I know I did it correctly, I can add them together and get my final answer of -233. When you're doing Hess's law, make sure you're not just doing the reaction part like this right here and figuring out how to add them together, because that's not the point. The point is to figure out what delta H is, or delta G, or K. So make sure you're keeping going and getting that number that you want. You put so much work into the adding, sometimes you kind of like, oh. All right, so one more Hess's law. This one, they do not give you the overall reaction. You have to write it out. It's a formation of HCl. So we know this will be 1/2, and so will this. H and Cl are both diatomic. All right, so we can start with whatever one we want. I don't think I would start with the first one. And the reason is because there is H2 here, and that is in our overall reaction, but H2 is also here. So that doesn't seem like I'm not going to know exactly how to do that yet. So instead, I'm going to just start with HCl. You could start with Cl2. That's also only in one place, but I'm just going to start with HCl. And what you'll do to this one is just flip it. So I would take and then my delta H will be the same thing, but positive. And then we can do Cl2. We're just going to multiply that second one by 1/2. And then do the same thing to delta H. And now I can go back up to the first one and figure out what to do with it. So you can go back to H's and figure it out, but I'm going to use N2. N2 right here needs to cancel out here because we do not have N2 in our overall reaction. So I'm going to flip this and multiply it by 1/2. So now when I do that, the NH3s cancel, NH4Cls cancel. We have 2 H's here and 3/2 H's here, so this will go away, and this will become 1/2. And then the N2s will cancel. So I'll end up with 1/2 H2 plus 1/2 Cl2 gives me HCl, which is what I want. So my delta H is this. And that's it for Hess's law practice. Now we'll take a look at some of our other things that we've been talking about in this unit. So this reviews our conceptual questions from the last video. We saw tables like this already. This is asking a little bit of a different type of question. In which of these 4 scenarios can you tell whether it is thermodynamically favorable or not? Okay, all it says is which ones can you know about it? So you can know about it in the second one and the fourth one. In the second one, you have a positive delta H, so that's unfavorable, and a negative delta S, also unfavorable. No matter what we do with temperature, it is going to be unfavorable. For number 4, they're both favorable, so no matter what we do with temperature, they are both favorable. For the other 2, it really will depend on the temperature. So here we have a question relating to delta G, okay? Based on the information they give us, we're going to use the Nernst equation here. But we don't need to have the two delta G's, because it doesn't say that we have any sort of non-standard conditions here. So you can just use this regular one, which is on your formula sheet, I believe. Okay. So all you have to do here is plug in your numbers. You'll notice that it's not ln Q, it's ln K, because as far as we know, this is all at standard conditions. So we're going to plug in our R. Remember to convert it to kilojoules instead of joules, because we want delta G to be in kilojoules. I mean, I guess if it was open response, you could do it in joules, but here they're all in kilojoules. So, and then we'll do temperature, but remember that has to be in Kelvin, so 298, and then the natural log of the K. And there's your answer. Next question we've already talked about in the last video, so it's just a quick review. Can every non-spontaneous reaction be spontaneous by adjusting the temperature? And we know the answer to that is no. Okay, if both delta H and delta S are unfavorable, then changing the temperature will do nothing to change favorability. Okay, so if delta H is positive and delta S is negative, there's nothing we can do. It's going to be unfavorable. So this is another conceptual question. The reaction below is not spontaneous at room conditions, but becomes spontaneous at higher temperatures. So it's a little bit of a flip from some of the ones we were looking at in the last video. Okay, so what this is telling us is that at room temperature, because that's what the question is asking, we know delta G is positive. It's telling us it's not spontaneous, so delta G is positive. Okay, we also know that if we increase this temperature, it becomes spontaneous. So that means that delta S must be positive. It must be favorable, but not when the temperature is too low. It doesn't matter. Okay, so like you have to know that is also positive. And if we know delta S is positive, the only way it could be not spontaneous at room conditions is if delta H was also positive. Okay, so it's a little bit of a conceptual puzzle for you to figure out, but you just need to think it through, and then you will find out, you will realize that they all have to be positive. All right, a few more questions about these numbers. Which parameters below correctly describe the condensation of water on the inside of your car windshields? Delta G will be negative because it does spontaneously happen. It is an exothermic reaction because we're going from gas to liquid, so we know we release energy. If we were going from liquid to gas, we absorb energy. That's endothermic. But delta H is going to be negative here. Delta S is also negative because we're going from a more disordered gas to a more ordered liquid. And then you've always known that gas to liquid is going to be a negative volume change. So they are all true here. So here's another conceptual question, but this time it's about bond enthalpy. Okay, delta H for the reaction below is negative. Negative 97 kilojoules. Doesn't matter, you don't need to know that. Which is larger in magnitude, the bond enthalpy of the reactants or the bond enthalpy of the products? Okay, so remember that bond forming is exothermic, which means delta H would be negative. Bond breaking is endothermic. So in this case, if we know that delta H is negative, the bond forming must have a greater bond enthalpy. Okay, and they're talking about magnitude, so we're not looking at, trying to figure out which one is bigger or larger. We're looking at magnitude. So we must, since the bond forming is the one that releases energy, the overall reaction releases energy, we must know that the products are going to be larger in magnitude.